Hello students, this is the time to have a brief introduction about the Bra-Ket notations and commutators. As we have already studied the basic one-dimensional problems, infinite potential well, finite potential well, potential step, and potential barriers, and have seen how the wave functions there are, how the wave function are, how the probabilities are. So now we will have a little bit of Bra-Ket notation first. So don't worry about it. There is nothing to get feared of. So let's say, what do we do? Let's say we, in a simplistic manner, we discuss this first, and later, when if we do the formal, proper formalization of quantum mechanics, then we'll do something more. Simplistic notation. Writing a wave function is as equivalent as writing a ket. Writing this is called a ket. Something inside this is called a ket. This is nothing but a wave function, let's say. And when we do a complex conjugate of wave functions, this is called a bra. Something is called a bra. Well, when we do a integration of psi star psi, it is as equivalent as writing psi psi. It will do some different functions. It is as equivalent as writing as psi 1 psi 2. If this is 1, then of course, simple normalization is 1. In a Bra-Ket notation, I write as psi psi is 1. So I should write it there. So left hand side, all the general quantum mechanics integral notations, what we have studied so far. And here on the right hand side, it's a Bra-Ket notation. Bra-Ket notation. So if you do an expectation value of, say, you are calculating an sorry, we should have a star there. Psi x. In a Bra-Ket notation, you get it like psi x. Or any operator. I didn't do a formalization of all operators, but as you know, there is a momentum operator and kinetic energy operator. So here we have space. So momentum K. So we write, say, psi minus ix. Sorry, IH bar del x over psi. This is as a function of x, this is as a function of x. This in a Bra-Ket notation could be psi px psi. As I know, px is this. if you write kinetic energy, which is you also know h square by 2m, let's say total energy, kinetic energy is just p square by 2m. Let's say it's Hamiltonian. So say Vx. You are trying to calculate the expectation value of Hamiltonian here. The same thing I can write in a bracket notation just like this. Hamiltonian is in one dimension. So guys, these are the bracket notations. We'll use it again and again, and as we do the operators and their representations slowly, one by one. So we'll all use bracket notations, don't worry. So these are simple integrations and expectation values of momentum and the energy. So these are small notations, just like writing this. Better to write to have this. This is not as easy as this, but okay. For a starting introduction, we just, whenever you will see psi and psi, you just imagine this would be a conjugate of wave function, and this is a wave function, and then we have a integration of that. So all the basic notations are there in front of you. I can give you a brief table there. Okay, let's have a table for your convenience. Okay friends, so next it's time to have a brief overview of operators and commutators. We'll come back to those concepts later also. But okay, what is an operator? As we see that when we do a psi star, say minus IH bar del psi del x integration, here we are calculating expectation value of Px, which is minus h bar x, Px operator, that is operator, over wave function I. So now if you think like this, that we have a psi, we are operating Px over and wave function psi, and at the left you are operating another wave function in terms of complex conjugate, that is in terms of bra. So this is as equivalent as this. So think like this. You are differentiating psi. Think like this. You are differentiating psi and multiplying minus IH bar with it, like minus IH bar del psi del x. It's minus IH bar del x psi. This is an operation. that differentiation and multiplication with minus h bar. This is an operation, and that at left hand side psi star and that integration, that is also an operation, but that is an overall operation, that is not an operator. So okay, so we have a psi, you are applying px over it, you are getting some another function, then you are multiplying at the left once again with psi and operating a psi bra at that left of that px psi. That is okay with it, and that means that automatically implicit that we are doing an integration. Till now we are only doing that integration formats. So okay, so that's an operator. You will come across many operators, but right now we are concerned with 3 operators. Your px is this, expectation values also, and you calculate expectation values. So I shouldn't write psi here. Kinetic energy is, of course, and Hamiltonian is of course this, plus Vx, the total energy operator. So okay, you say that this is the 3 operator we initially start with. You know the calculation of expectation value already, no problem. So this is an operator. We will do that operators. We will deal with all the operators, and in quantum mechanics, when you calculate anything which is real, which is kind of something real, that the value of something can be measured, like the momentum, that kinetic energy, these are some real. This is not like this is something which we can measure, which we can have real experience with. That is the momentum, that is kinetic energy, that is the total energy. These are the basic operators. Okay. Then you know that you know expectation values, right? Like if you are calculating an expectation value of x, you are actually calculating psi over some wave function x, another wave function. That is an expectation value of x. Expectation value of x square is nothing but psi x square psi. And if I write in bracket notation, so this can be written as just like this. And px also, we already wrote 2 times. This is yes, expectation values. Get over like this. You can just have a square. So you got a square of that. So these are expectation values. They have some real, something real. So in exam, you will need to find expectation values. Many times, given the wave function. The wave functions will be given, and then you need to find the expectation values of some common things, like which may be x square, some px square, or anything. While doing that, when doing the integration, check odd, even. If the integral is odd, the integration will be 0, and general Gaussian integral formula, which I have already told you, I told you at the wave packet class. Okay, so this is a brief overview of expectation values. Now let's have a brief recap on the basic infinite potential well, and let's learn something more about the operators. Okay, so these are what we learned is the bracket notations, how to write things in bracket. We'll do the examples. This is a little bit of table. Okay, then I wrote the operator. What is an operator? Not a formal definition here, just a differentiation can be an operator. Okay, you are differentiating a wave function in a particular manner, and I'm telling you that this is your px operator. We defined that px a long ago. Then the procedure of expectation values calculation we already know. Then just a notation with the bracket. So now I go to the Schrödinger equation first. So let's have a brief recap. I have told you that the time dependent form was like this. It is time dependent, and each psi is each psi. It is time independent. And I write in one dimension, h psi is like this. Some potential, it is e psi. Okay, so you can write this in bracket notation like this. H psi is psi, h psi is e psi. That's it. Okay, here I tell you some properties of time independent Schrödinger equation solutions, time dependent Schrödinger equation solutions. We just have a recap. You can pause here or quit here and go back to the initial lectures of the Schrödinger equations. Here you can imagine like an Hamiltonian operator operating on the wave function gives you some constant values. By constant I mean it's not changing with respect to position and time, x and t, and give you that psi back. H operating on psi gives you psi back multiplied by energy. You can think it like this. Then I say that each operator operating psi, if you E psi, that E I called you, I tell eigenvalue of, is my recording on? Yes, okay. Eigenvalue of operator H. Any operator operating over operator, till now operators are differential operators for you. Later on we'll see that operators can be matrix also. So okay, let's forget about all of this. Just focus on what I'm telling you right now. Any operator operating over a wave function if gives the wave function back multiplied by some constant, like this operator A operating over psi, give you some constant A, that psi back, then that A, that constant is called eigenvalue of operator A over that particular wave function. Okay, you may find this is pretty abstract, but this is not. This is not a very abstract thing. So okay, let's give you some example. Let's give you some example. Suppose infinite potential well. You got that wave function, a set of wave function we already evaluated, and for energies okay. Yeah, the problem, the whole problem in quantum mechanical term is this. And when any psi n you take it, say I take psi 1, and Hamiltonian we just have a minus h bar square by 2m del square del x square, no potential energy is there. This is not the complete Hamiltonian. We have an interesting story over there. So okay, let's for the time being, let's say h is this. So that means if you are operating over any psi n, what you get? Del square and d square is same here, because psi is the function of only x, no other functions are there. So if you take a double derivative here, what you get? That 2 by L comes here. You take a 2 times derivative of sine, that give you n pi by L whole square. One sine will give you 1 minus, and that 1 plus cos, then that plus cos will give you a minus sign, so that minus cancels. So, and then again you get this thing back, the sign back. Okay, so here as you see, you get h bar square n square pi square 2ml square multiplied by this. So that's the crux of the procedure, that h operating over psi n gives you en psi n, or in terms of Bra-Ket notation, the same thing you get. The same thing you get. So, okay, friends. So what did we learn? We learned is there is something called eigenvalue, h operating on any wave function. We already solved it. So these wave functions, if you have your h as this, then this operates over this wave function, gives you this. This is analytically just we have calculated, give you this energy and that psi n back. The whole Schrodinger equation I have told you earlier is called an eigenvalue problem. H operating psi gives you psi back multiplied by the energy. So these energies are called eigenvalues. And these wave functions operate like these wave functions. These are eigenvalues. Let me tell you another term, that these wave functions over which that Hamiltonian operates and gives you that same wave function back multiplied by a value which is called eigenvalues, then the wave functions are actually called eigenvector. So these wave functions are called eigenvector of Hamiltonian, and it's called eigenvalues of Hamiltonian. Schrodinger equation, eigenvalues, and this is called eigenvector. So we'll use these terms very frequently, so let's get used to it. So now you shall forget all about h operating over its eigenvector give you its eigenvalue and that eigenvector back. Any nth wave function, this is a general psi, give you nth energy eigenvalues, that eigenvector. So this is operator, this is eigenvector, this is also that psi is eigenvector, and that I better delete it. This is eigenvalue. So the whole quantum mechanical description of a problem is an operator operating over its eigenvector, give you an eigenvalue and that eigenvector back. Every function is not an eigenvector of every function. That is good. That is to be understood. That I tell you that this is a solution of a Schrodinger equation. So that is eigenvector of this. any function is not eigenvector of this. Say e to the power minus x is not an eigenvector. Is it not? Think about it. Okay. If you operate double derivative over this, you get the same function back. So in that sense, it may be an eigenvector of this, but okay, sure, it's not a solution of Schrodinger equation. So let's better tell like this way. That will be more clear. Because if you see double derivative over the power minus x square, you get it some function of x that is not expected. This to be an eigenvalue or an eigenvalue is not a function of anything. Function of anything. Not anything, function of space and time. So okay, so hence this is not an eigenvector of this. If you given an analytical form of an operator, and if you given an function, just like I told, let's think about e to the power x wave function, and the operator is the same operator. So if you do this over e to the power minus x, so you get just a -1, then you get another -1, so you get a +1 e to the power minus x. So in that sense, surely this operator gives you the same thing back with just a constant over there. So in this sense, say that's KE operator, or if I say that Hamiltonian operator operating over e to the power minus x gives you that back. So in that sense, e to the power minus x is an eigenvector of h square by 2m d square dx square, but not a solution of Schrodinger equation. So it is not an energy eigenvector. To be an energy eigenvector, we must have E psi solution of the Schrodinger equation. But that solution of that Schrodinger equation is given by this. So you are confusing, because the whole differential mechanics, the whole differential equation problem is a particular case where you have to satisfy a differential equation together some boundary conditions also. So if you say, why sir this is not a solution of this, it may be a solution with this particular energy eigenvalue, I will tell you, okay fine friends, but that eigenvalue problem still have to solve a boundary value problem also. So that e to the power minus x does not satisfy the boundary condition. And that boundary condition is what? Wave function must go to 0 as x go to plus minus infinity. That it does not satisfy. It diverges as x goes to negative infinity. So this cannot be a solution of infinite potential. Well, so now let's go to the infinite potential well problem. Once again, I'm writing some situations and rewriting them in terms of bracket notations so that you will have a good idea about what I'm telling. Say we have an infinite potential well, and I'm saying that the wave function is at, say, this is the first wave function, let's say pi x pi l. Let's say I assign this as 1 by root 2 there, and let's say I assign the second wave function first excited state. This is the ground state, this is the first excited state. So, okay, you can write it in terms of like this also, that is better. I'm writing the same thing in 3 notations, and that is okay. This is not a new notation, just identifying that this is psi 0 and psi 1. And then many times you will get notations like this. This is the usual way to have a bracket notation. Okay. Expectation value of energy over this state. The state is very simple. You get this is these are the constants. So still if you just do this, you will get what? You will get these constants. We did this earlier. 1. So, and E0 E1, you know, this is pi square h bar square by 2ml square. E1 is 4 pi square h bar square 2ml square. You can verify it. It's a general rule that if your psi is C0 psi 0 plus C1 psi 1 plus C2 psi 2 that expectation value of energy or anything, any other operators also will generalize this. So this will be C0 mod square. We have a psi star over there. As this is a real wave function, so it merely matters. I write the same thing in bracket notation like this. Same thing, exact same thing in bracket notation. We have a YOLO pin there. that psi is C0 psi 0 plus C1 psi 1 plus C2 psi 2 inside a Ket notations. And then this part, the second line, I write psi h psi, that's the expectation value. I shouldn't write this E here actually. E is the energy, so I should write the Hamiltonian here. So, okay. So that part will be C0 square E0 C1 square E1 C2 mod square E. Oh, sorry, I wrote this wrong. These are E0 and E1s. Okay, so how this is working in Bra-Ket? It's simple. If your psi has, say, C0 psi 0 plus, say, C1 psi 1 to state, I operate a Hamiltonian over this psi. So I write Hamiltonian over this state. And I break this state and write here, say C0 is a constant, so H operating on psi 0 plus C1 H operating on psi 1. And then I know when H operates on any function, any eigenfunction, we already solved it, it's give you the nth, it's the nth wave function, it's give you the nth eigenvalue, and that will function back. So we need one more line of space here. Let's see. Let's have a line here to separate it out. Okay, then it will be C0, H operating on psi 0 will give you E0 psi 0 plus C1 E0. Now what? Now at the left, I need to operate that psi bra. That is the next part of that algebra. Okay, I get to copy here. Now what we do is, that is okay. Now I need to operate psi over this h psi. That h psi, and this is as same as and that h psi. This part I have already got this. Sorry, this is E1. I do lots of silly mistakes. If you do the same, you will you will not qualify in the exam. Okay, so that psi, I will write it like this. If my psi is this, when I write the psi as a bra, I need to write this. So psi is this. So then if say if your psi is C1 psi 1, say, or C1 psi 1, then its bra equivalent is psi bra will be phi 1 and this, and C1 star here. So if your psi is C0 psi 0 C1 psi 1, then your that psi bra will be psi 0 C1 star. plus psi1 c1 star. Okay, so then that psi bra, write this here, psi naught c1 star plus, sorry, psi naught c0 star, again a silly mistake, psi1 c1 star multiplied with this. Better to write it here. Get to use it. Okay, I just need to remove that equals to sign. So this multiplied with this, that was h psi. So this is h psi and this is psi. This operating over this. So now you get psi naught C0 star C0. Of course, a E0 also there, plus psi1 C1 star C1 E1. And what you need to know about that orthogonality in terms of bracket notation, that means that your psi0 is 1 equals to any n, and your psi0 psi1 is of course 0, like any psi n operating over psi m. These psi n psi m's are the eigenfunction, energy eigenfunctions, that's square root of 2 by L sin n by x by L equals to 0 when n not equal to m. So that means we got C0 mod square E naught plus C1 mod square 1. That's the entire story in bracket notations. I hope you got your concepts better now. I finish this slide to just I finish this slide by just saying the normalization condition. Everywhere I should have this the summation over all the Cn square or C1 square, which is actually nothing but C0 square, C1 square, C2 square. This should be 1. That is normalization. When I'm writing this normalization conditions and the energy, everything, everything I have written here, assume that this normalization condition to be true. If this normalization condition is not true in your given case, you need to normalize that. Suppose these are some things you need to be very careful. Suppose I say you are given a psi which is say 2 by 3 of psi 2. This is say energy eigenstates, and 1 by 3 psi 4. Initially it might look like that it is normalized, but yeah, but this is not. This is your say C2, not other constants as 0. This is say your C4. So what you need is C2 square plus C4 square here. This is 2 by 3 whole square plus 1 by 3 whole square. This is 9, this is 4, and this is 1. This is actually 5 by 9. this is not equals to 1. So to have a normalization, you need to divide the square root of this. So as 0 cn square have to be 1, multiply psi with 3 by 5, better to say 9 by 5 square root. So then psi normalized, initial psi by psi. This is actually any psi is cn square. Of course it is as psi. If you see, if any psi is cn psi n, and if the psi n's are normalized state individually, that the psi 2 and psi 4 are normalized, then of course this is cn square, which we have already proved in here also. We got a h, so we have e0 e1 square, all are there. And if you don't have h, simply this is just you just verify. These are very simple things, but at that initial stage these are to be done. So operate psi and psi, do it, prove it to be 1. Sorry, very sorry. Prove it to be cn square, sum of it. So okay, so that psi normalized is your original psi by mod psi actually. So you may write it in this format also. So this is this. So we multiply with root 9 by 5. That means we are dividing with square root of 5 by 9. So then your psi normalized is square root of 5 by 9 to 3 psi 2 plus so if you write everything inside the square root, so you can get 4 and 9 back. So I don't think you should get that 3 and 3, so you write 9 and you write this as 20 square root of 20, and you can write at this is square root of 5. No, I think I did some mistake somewhere. This 5 by 9 was okay. No, I 9 by multiplied with 9 by 5. I don't know, somehow I put it as square root over there. So I'm really sorry. That you need to divide by it by that multiplication. Okay. No, initially what I did was absolutely fine. So I did some numerical mistakes. So everything was okay. Okay, this thing actually I did here a mistake. Square psi normalizes psi by square root of psi star psi, square root of that modulus of square. So that normalized will be 3 by, multiply this by 3 by root 5, 2 by 3, shy 2, then 3 by root 5, 1 by 3, shy 4. Now you see this is properly normalized. Many times you need to do the normalization. Many a times you will need that. So okay, we were doing everything in Bra-Ket notations. That is good for us and good for our latter teachers also, good for you also, good for everyone. Okay, so we did that normalization, but still we haven't told you about what is a commutator. So now I'm telling that. So basically right now we know what the Bra-Ket notation is, what the expectation values is, how to use Bra-Ket notations in the basic quantum mechanical knowledge we have. Then we know the normalization, we know what is an operator, we know what is an eigenvalue, we know what is an eigenvector. So next part is commutator. Commutator is basically if you write A and B, two operators, you will have AB minus BA. That is a commutator. A commutator of A and B commutator of A and B. All these things are of profound significance. We'll do as we proceed. We'll do the significance slowly. Is basically AB minus BA. That means A operating over B minus B operating over A. So this is an isolated form. So if you say AB over psi, it is AB minus BA. These are operators. Operators we write most of the time in capitals. No, every time we write in capitals. And it is better sometimes we need to give, we'll put a hat there. But even if without hat, if you're writing something in capital, in my usual notation, it is just an operator. So okay, I write this AB psi minus BA psi. So AB operating over psi, BA operating over psi. You can write it in this way also. A operating over B psi minus B operating over A psi. Everything is fine. In terms of Bra-Ket notation, this is absolutely AB psi minus BA psi. And this is, you can write it also as B operating over psi, give you also an wave function Bra-Ket minus B operating over A psi. All these are same thing. Okay, so we can have some very simple relations among that operators. But before that, I would like to tell you what is XPX commutator. That's the first thing we do here. So as you see, X, the PX is minus IH del X. So as an operator form itself, as a differential form itself, without operating on over any wave function, I can write it as X minus IH del X minus IH del X over X. Now it might be of some confusion to you, but okay, we need to deal with. Whenever there is if we are not writing any wave function here, if right side there is empty, we just write this is just like this, and this minus minus plus. And if right side there is an x or something else, some function of x, we are not writing psi here. So just you get operated, del x, what you get? You'll get, sir, I get it 1, but no, we have something else there. So that's why it's sometimes difficult that you are just operating it and writing it 1, but you are missing another term where x will be constant, and that part goes right. So how come this be? Because there is another function at the right hand side. Okay, don't worry about it. I I will show you. So okay, I missed that x. We had an x. So this part and this part cancels. This part give you 1, and this is just IH cross. So I conclude here that x px is 1. So you might not be accepting my this line. Okay, so let do it another way. Let's have a psi here. Now what happens? So you are dealing minus x IH cross del x first, then second, minus of minus, so IH cross del x, there is a psi there. So actually what you are doing is del psi del x is the differentiation. That's IH del x operating over that x psi. Need to have a little bit of space there. So here I get minus IH x del psi del x, plus we have 2 lines there. Once it's operating on x, giving you psi back left hand side, that del x over x, plus at that next time that x comes left, del psi del x. Then you see this and this cancels, so you get IH psi. This give you 1. So hence what we get is once again x px operating over psi give you IH psi. Then I tell you that the commutator of x and px is 1. So we did it both ways. This is a slightly larger way, the yellow part, and the white part is easier way. But you might get mistakes because sometimes you might skip that there is a psi there. So you might get a wrong conclusion. The commutator of x and px is 1. So you can calculate commutator of any combination of x and px. That is very easy algebra, and that's very similar to the matrix algebra itself. I'm not yet going to the measurement problem and the knowledge problem. Yeah, measurements and knowledge problem is a very much building block. It's a very basic building block of the quantum mechanics. So have a little patience. I will do it. But right now I need to do a slight algebra. So if you have say A and BC here, two operators, is my recording on? Yes. That means ABC minus BCA. Then you can write ABC minus the ACB plus minus BCA plus ACB. We are just subtracting ACB and ACB here. So did I do it right? I got A B A B C. No. I got A B C. What I need is A B C minus B A C. Okay, that C is at the right. B will be at the left. Okay, minus BCA plus BAC. Simple. BAC and BAC, I just added and subtracted. So what happens? Then I get AB minus BA. At right hand side it has C. Here at the left hand I got B common. CA minus AC, or rather plus AC minus CA. So this will be A commutator B C plus B A commutator C. You look the position of C and B here. C at that right, so C at that right. B at the left of C, so B at the left of C. Don't forget it. You get AB comma C. You proceed similarly. ABC minus CAB. Now you get ABC minus ACB minus CAB plus ACB. Now you got A common, BC, and here you get B common at that right hand side, so plus AC, as similar as the previous problem. I skipped one step intentionally. So like this, you proceed. ABC commutator plus BCA commutator and a commutator, then CAB commutator. This should be 0. Verify it. This is called Jacobi identity. I just give you one step. So A commutating with BC minus CB. You do the rest of that step. That means A commutating with BC minus A commutating with CB. Now use this. Now use the left formula and verify. This is have to be an exercise for you. And just I add up if it's A and it's B plus C commutating. Whatever the combination of B plus C is, this is always AB plus AC. Just like this, we have A commutator BC minus CB. I divide it in two parts, ABC minus ACB. So these are the very simple algebras, and what we'll prove later on, we can prove it here also, that if any function of say x commute with px, what happens? and if any function of px commutes, I didn't mean commute, but the commutator of x with any function of px, what happens? Think about it. We'll do it later also. Expand fx if px in a series, in an algebraic series. Any analytical function should have an algebraic series. You can take a Taylor series, no issues. Definitely we'll have a Taylor series. It's an analytic. Let's assume that the derivative exists. The derivative of x continuously exists. Derivative of the px, that function derivatives continuously exist. Then you should have a Taylor series of that. Then you can definitely expand and think about it and take it as a homework exercise. Okay, friends. Then we have a good amount of knowledge. You can calculate commutator of many possible things. There are many questions comes. One very common question is x square and px square. If you have both x square, so you get better to write like this: x and px square. Then you do x px square plus x px square x using ABC. Just if you forget, then look, pause here, look at that previous page. So the second one is this. So then you again divide it. Then you use x px. Sorry. Then you write it as px. Write it as x px. This is the most crude. This is the most crude way we could do this. And x px again, you can use x px here plus x px here, x px. That x was common, so you can take x common and it will be better for your understanding. Plus similarly that x px plus x px, but here this time px at that left hand side, whole multiplied with x. So then x px is I h bar. So what you have, I h bar px plus px I h bar plus I h bar px plus px I h bar, have x. So you get 2 times of x px pxx pxx. Do remember always that as x px minus pxx is 1, sorry, is I h bar. That means as x px is 1, so never take x px and pxx as same. They are not same. They are not same. They are different. In quantum mechanics, the order of operators is very important. That whether you x first or px first is very important. Xpx is not equals to pxx. That's strange, right? Okay, okay. So we have elementary ideas about how to evaluate the commutators. Should I proceed more in this class? I don't think so. Give me 1 minute of time to think about. Okay, I should stop this lecture right now. Let me do some harmonic oscillator in the next class. Thereafter, I should proceed towards angular momentum. No, before that angular momentum, I should have another lecture about that measurement problem, measurement postulate, better to say, and conjugation of operator. That means we have discussed Bra-Ket notation, that bra is a conjugate of ket, but operators also have conjugations, and there will be some interesting mysteries to be solved there. So that operator conjugation, that means that dagger, the strange dagger symbol, you might have already noticed somewhere, strange dagger symbol over operators, how that comes and what is it and what is the importance and implications, that will be discussed. But before that, we should have an analytical and some operator solution of a harmonic oscillator, solve that problem completely, do that wave functions, everything, then measurement postulate, then go towards angular momentum. So okay, this is a quantum mechanics 1 course. So very very deep formalism might not be necessary, but okay, some formalism is always required. Okay, yes, my friends, bye for this class. Come back very soon.